I have a question to the part where you printed these graded index waveguides or step index waveguides. In any case, polymer in polymer kind of waveguides.
Yeah.
So you certainly know that there has been a large community of people writing waveguides into glass, silica glass. So how do your results compare to these in glass writing results?
So in glass writing results, one has to, I would say, first separate two different strategies. One is modifying refractive index, and the other one is creating a void, essentially a vacuum, defects, because they perform rather differently. Regarding refractive index, with the refractive index modification in direct glass writing, we are getting very comparable. Losses, we are still a couple of dB away, but not too much. If you compare it to the ones where they use really defects, then of course we can't compete with the confinement because the refractive index contrast is significantly higher, and therefore bending radii, etc., they go lower. So a denser integration would be possible. One of the big advantages of that concept here is, I would say, that it's additive. So, you know, you can take your silicon circuit, you put the resin on top, and then you write on top, directly aligning to the substrate, etc. And the other feature is this, especially this dip-in procedure, where if you write directly in glass, you always get the aberrations of going through a solid, and you're also limited by the working distance of your microscope objective. So there are several really advantages, I would say, to this concept. And in terms of pure metrics, if you do not consider the void kind of glass inscription, I think we're getting comparable.
Thank you.
Thank you, Martin. Do we have more questions? So let me ask you a few questions regarding this losses, because that's the stuff that usually I do not care too much about the losses.
No, you don't.
for my applications, but here it's crucial in your applications. So you select basically one wavelength, operating wavelength, in all these setups, and I was wondering if you have scanned through the different wavelengths to try to identify in a way the origin of the losses that you get inside.
No, so that we haven't done. We are starting to do investigations where we try to see the different scaling of volume versus interface area to identify if this is a volumetric or interface effect. Well, you and me, we try together to build numerical models, but there essentially we are hitting a wall regarding combining Boolean combinations of complex shapes in STL files to model the effect of surface roughness. So at the moment, I can't really give any conclusive answer here. It's would be speculation. What we see is that if we increase essentially the so as you could see before, for single mode propagation, you have access to a range of parameters. And if we essentially map the losses through these, we do not appear to see an effect of volume. So that would tell me that at the moment we are interface limited. Okay. But that is a, let's say, you know, a very careful first order statement. Yes. So this is for sure what we're doing right now also, but we're trying to find ways how to do this.
Okay, thanks. I just look at the public if there is any more question. Yeah, Martin?
Yeah, this is more of a comment to a possible origin of the losses in these waveguides. We have lately been doing some also in situ optical coherence tomography of printed structures or during the printing. And one simple observation that we have made that has surprised me is that the monomer itself, the photoresist, is not perfectly homogeneous. It has blobs in it, as we call them, inhomogeneities in space that are not connected to humongous refractive index changes, something on the order of maybe less than 0.01, but they are there. So I would think that these variations also translate into the printed structure that is after exposure. And maybe that is one source of losses in your structures. We typically don't care because we do not look for long-range propagation of light, but maybe that is in fact important for you. If you care, we could have a look at your printed structures with our optical coherence tomography setup and characterize that. Just an idea. I'm not sure this makes sense.
Yeah, we try to go along this line as well. So we try to do some micro Raman, but this was just, you know, in terms of time consumption was not feasible. What we see here, we found surprisingly or interestingly, we found some very similar effects in the holographic characterization by the EPFL, where both for the non-developed and the developed samples, we found variations, and they are larger than essentially the printing power fluctuation. So this would confirm it. The problem with the holographic characterization is essentially you integrate over the depth. So these differences, they start to wash out. But I think so we never got high enough quality data to publish this or submit this, but it seems to go into the same direction, yes.
Yeah, with OCT, you would see the, so to speak, the refractive index in all 3 dimensions mapped. And with modern setups, it takes you on the order of 1 second to get a full 3-dimensional stack.
We tried this with micro PL, with micro Raman, and that was at 90 seconds per voxel. So then, yeah,
that's what I'm saying. So OCT, state-of-the-art OCT has become pretty fast.
Okay, that's great. Thank you.
May I just ask, Martin, you said a refractive index change in this inhomogeneity on the order of 0.01. On which resist was this?
That was actually with IP dip.
Okay. Because in this gray tone lithography that Daniel is doing, I mean, you don't have a much bigger optical changes in actually between the outside and the inside.
No, I mean, you can see here on this slide, you can actually see the delta N. Oops. And you can see the delta N, which we are trying to create. So we are usually somewhere 0.3 times 10 to the minus 3.
Yeah. So this could be a 30% error.
These blobs or these variations have been surprisingly large to me. I didn't expect anything like that.
And on which feature sizes, on which scales, like hundreds of nanometers, or which kind of physical scales do they happen?
No, they are rather on a diameter of a couple of microns scale. In our OCT setup, we don't have nanometer resolution anyway. The resolution would be 2 microns, roughly speaking, in all directions. So, but these objects are resolved. They can be pretty large, actually, and I'm not sure what that is. I think these are some oligomers that have formed by thermal activation, or I don't know what, but they are in there.
Yeah, it is interesting because we also dope polymers, the IP dip, with other materials, and we find also that this homogeneous dispersion is difficult to achieve in general.
I mean, there may be ways to get rid of these blobs by some processing of the photoresist, by pre-filtering or what. Maybe that is then important for what you are doing.
Yeah, I mean, to be honest, I'm more interested now in making the devices reconfigurable, and then, yeah, there's a lot of other interesting things to do before I would start tweaking a lot on the fabrication details.
Yeah, I understand.
But I mean, it's very interesting to know where they might come from, because it's for sure something we're looking into. Thank you.
Do we have more questions?
Yeah, I've got a naive question. I think you are interested also perhaps in photonic crystal fibers.
We are interested in photonic crystal sections, yes, but there's groups doing this work. So people have 3D printed photonic crystal fibers, fiber splitters, doing polarization filtering, etc. Yeah.
But do they couple this to some kind neural network algorithm to actually improve the properties, you know, of...
You mean for the design of the photonic crystal?
Yeah.
No, so that the work I have seen was rather standard classical honeycomb kind of lattice arrangement around the core of yeah, essentially empty photonic crystal structures. Yeah. So there was nothing really very sophisticated going on in terms of design.
Because surely, you know, so of course for the leakage, for leaky modes, very small perturbations in the position of the air holes in silica can lead to tremendous changes in the imaginary part, for instance, of the frequency, and so your leaky mode will propagate on longer distances. Yeah. So I guess that the neural network might possibly be trained and kind of, you know, no.
Yeah, I mean, there's a lot of, so let's say this goes the other way. Instead of doing neural networks using photonics, there's a very big activity right now in the other direction in photonic system design and optimization, using all kinds of machine learning algorithms for optimization, using neural networks or genetic algorithms or, a lot of different optimization tools. But yeah. So I follow this work. I haven't seen this particular kind of optimization, but we have not explored this in our group.
You are not looking. And are you looking in some kind of topological properties also of optical elements, or not quite yet?
So I am in contact with people working heavily on this, and we are, let's say, this is one vision for sure. So this is mostly, for example, Mercedes Kayavikian, which now moved to Los Angeles, and Dimitri Chrysolides, but this was more like two years ago. We had active exchange on this topic. At the moment, we focus on the waveguides and then to realize the topologies. So this would essentially be active photonic topological systems where we have lasers, etc., and not, let's say, the simple, you know, not the linear propagating kind of systems where you do modulations of a waveguide to create coupling terms, etc. But I mean, there in there's so Alexander Zamait or other people are working heavily on this, and I think I find the topic interesting, but me personally, I'm not the expert in this, and I'm not focusing on the topological systems at the moment.
And you have been interested lately, or well, in the past, in Brio-Wind scattering, in this kind of stuff, or?
Me personally not, but no. Someone else in our department.
Okay, but you don't really work in this area or interact much with these people?
No. So for my focus at the moment really is to realize a scalable, fully programmable SU2 kind of unitary matrix operator, because I think there is a very large number of applications for this. And then they of course feed into all of these kind of system emulations, let's say topological system topologies, etc. So this is why I think this kind of strategic tool is what I would really like to demonstrate.
And going back to the very first slides where you showed, this doubling every 3 to 4 months, You mentioned that this was not sustainable for the planet. Can you just say more about that? Because you said these are big words, but can you just be more specific?
I mean, yes. I mean, the fraction of energy consumption now for ICT systems, so computing and telecommunication, it's reaching or significantly above 10% now. And neural networks are a very, it's a growing part of that, and it's a accelerating fraction of this. I mean, in this article, for example, what is really interesting on this is that, this was 2.5 years ago, and they're training a state-of-the-art system consumes as much carbon as the carbon dioxide as 5 cars in their lifetime. I mean, this is not 5 cars in one day; it's across the entire life cycle. Or we produce one of these networks training events of a competitive model uses more carbon than one person in a day, in a year, including everything. Eating, traveling, food, etc. So these are significant numbers. Problem is that they are such high-dimensional estimations. They include so many kind of predictions and abstractions that I tend to use them as, let's say, as a cliffhanger, but I don't want to argue the specific details. But I think the scaling is clear.
Mm-hmm. So in fact, really, artificial intelligence, these kinds of neural networks, it's not really the way to go for people who want to make some designs which are green designs.
At least not if you want to have the competitive solutions. I mean, of course, for example, if you use more simple networks for something, data pre-processing stages where you do not need this. I mean, this one here has, I think, 13 billion parameters. So, these are massive models. So then, of course, they use a huge power. If you just want to have a local processing of, for example, pre-processing of voices, images, etc., you would not need this kind of scale. But the energy inefficiency of machine learning approaches is well known. I mean, there's 6 orders of magnitude if you compare computational volume between the brain and the most energy efficient systems we have at the moment. But again, I would allow an error bar of 2 orders of magnitude in this kind of comparison.
What strikes me is that, people for the weather forecast, they use heavy computational resources. So those people looking in, simulation for climate change, they have a huge carbon footprint.
Yes. Yes, for sure. But at least then they do it for the right purpose, and not everybody needs to model the climate in their backyard, I guess.
Yeah, okay. No, I can't say that I understand all of the items of your talk, but I really enjoyed it anyway. Thank you so much.
Thank you very much.
Let me just comment that if you want to be fair, you have to compare the energy footprint of solving a problem by artificial intelligence with another approach that exists.
Yes.
To solve it by trial and error or whatever. Pick your favorite approach.
Yeah.
And then the question is, who consumes more energy? And this is not clear to me. Of course, there's also the option to just not solve the problem, and you also save energy.
Yeah, I mean, these are exactly the complexities. I mean, the other problem is also many tasks which you can now solve with neural networks. They actually have a positive energy impact because, for example, you get lost on your way much less because Google Maps tells you exactly where to go. So there's secondary effects. This makes this whole kind of estimation rather wishy-washy. Like, it's hard to really grasp it with very precise numbers. I think what is clear is that there's a very, very large inefficiency, which right now which we just swallow because we can start solving tasks. But if you want to make this sustainable, we need to get rid of them. I think that's the message. How much precisely is this penalty is very. I think it's a very there's a very large certainty associated to this comparison.
Martin has a question.
Yeah, Martin.
Yeah, maybe you don't want to answer that question, but I ask you anyway. You mentioned that one of the challenges ahead of you is to make these structures programmable, and I perfectly understand that. So what would be the approach to make it programmable?
Yeah, that's my $1 million answer and question, I guess. So I think I can answer this question by answering what I would not do. So I think a approach. So okay. So some kind of non-volatile programming, I think, is essential, because you don't want to pump energy into a configuration which you statically read by optical signal propagation anyway. So it would be some kind of, let's say, phase change element, memristive kind of element, which needs to provide this. The big question is how to address those. Because if you do a 3D circuit, and let's say we want to 3D print a mesh of Mach-10 interferometers to get this SU2 unit, then per interferometer you need two elements. I mean, in the end, every matrix element needs its physical representation. So there is no 3D doesn't mean they suddenly scale linear elements. It needs elements which scale quadratic with the number of inputs and output channels. And if you now would want to wire them, all of them, to an external control computer, then the entire scalability breaks down. So I think this is not the way to go. So what I essentially have my eye on is to program these computers with the same input and output channels which are provided. So essentially use signal co-propagation and to use kind of annealing concepts to set these weights. I mean, this is, if you at least want to remain in the neural network kind of concepts, optimization is iterative anyway. So it will never work that you, let's say, characterize this transfer matrix at one stage, do a simulation and implement a delta omega, which gives you the result. It will never work, because these systems are so high dimensional and there is uncertainties. So you will have to do optimization and approximation on the device. And I think because of this, a kind of iterative annealing kind of approach is what I would use. And there use also optical means and inputs and outputs. I think this is for me the way to go.
Thank you.
Okay, thanks, Daniel. I think we have done for almost half an hour of questions.
That's a good sign, though.
So thank you again for participating to the MetaMAT webinars.
My pleasure.
My pleasure to have you here. And your webinar has been recorded and it will be made available in the following days on the
Okay,
website.
great.
Thanks a lot.
Thank you very much.
And talk to you soon.
Talk to you soon. Bye-bye.
Bye.
Bye-bye. Have a nice day.
Same to you. Bye-bye.